We continue our discussion on principle or ellipsoid of inertia. So we got an equation which is this for any arbitrary direction. What happens is when this alpha, beta and gamma represents a direction of a principal axis where the I x y, I y z, all the non-diagonal terms vanishes. That's where the equation reduces to this particular form. Okay, and in this particular form, this one is the equation of an ellipsoid, because the general equation of an ellipsoid in a 3D xyz plane is a x square plus by square plus cz square equal to 1. So this is the general equation of an ellipsoid. So you see, we had an equation where all the cross terms were present. Now in a principal axis system, this particular equation reduces to this particular form, which represents the surface, given by an ellipsoid, right? Now in this system also, this is also an ellipsoid, but this ellipsoid where the axis system is not falling along the direction or different easy axis of the ellipsoid. What I mean by this is, let us assume this surface. So this is an ellipsoid. Okay, so we have all the axes marked. Now let us assume that this is the axis system we are working on it. Okay, so this is my x, this is my y, this is my z, right? So the surface which is tilted in this axis system is represented by this equation. Now when alpha, beta and gamma, they are the principal set of axes, the axis system takes an orientation. For this particular orientation alpha, beta, gamma, the axis system falls along the symmetric axis of the ellipsoid. Okay, so let us call it the x prime, y prime, or rather I would call it the capital X, capital Y and capital Z axis system, for which the cross term, because the axis system is now following the symmetry of this ellipsoid surface, all these cross terms becomes 0 and the equation reduces to this. So this is called the ellipsoid of inertia. Now if we have a system where we have certain symmetry present, for example if we have spherical symmetry, then I1, I2 and I3, all this will be equal to some value I, and the equation will simply be rho x square plus rho y square plus rho z square equal to 1, and that gives you a surface of a sphere, which is a special case of the ellipsoid. For symmetric systems, we will have I1 and I2 will be equal, and we will have more symmetry associated with this particular ellipsoidal shape and all. Also there is a important concept which is important in terms of for many practical engineering calculations, which is called the radius of gyration. Radius of gyration, which is defined as I is equal to m r g square. Let us take an example. If you recall, in the last class or one of the last classes, we found out we discussed about the moment of inertia of this uniform circular disk of radius r along an axis which is passing through its center and perpendicular to its plane, and we have found out that I for this particular axis is given by half m r square. Now radius of gyration is a hypothetical radius for which we can calculate for any object for any given axis if we know that I. So if I compare these two, now if I set this equal to m r g square, then we get r g, see m immediately cancels out, then we get r g equal to r by root 2. So this essentially means if we find out a length which is given by rg by root 2, now root 2 is 1.41, so it will be something which is shorter than rg. So if we find out this particular radius, and which is roughly this, okay, and if an object with mass m, which is the mass of this whole system, rotates around the same axis with a radius of rg, it will produce the exact same amount of moment of inertia. Okay. So radius of gyration is essentially a point mass approximation. It gives a good point mass approximation for any system. For any system, we can try to calculate an rg, which physically means if the mass of the whole system is reduced to a point, okay, and let us say this is my object and this is my axis of rotation. Okay. So we find out some value of I for this particular axis. Either we can calculate it for this specific axis, or we can take this, take the tensor for this fixed origin. Okay, let us say this is my origin, and try to project I, try to project this tensor along this particular direction. Whichever way we have found, we can find out some I value. Now this I can be equated with m rg square, and we can find out some rg which is equal to I by m whole root. Now this, what it means is, if the mass of the object is m and we represent this whole system with a point mass which is at a distance rg and rotating around the same axis, it will produce exact same amount of moment of inertia. So this is a very important aspect of engineering design, and we will take up maybe some examples, or I will give it to you in your assignment. Okay. Now let us move to the last problem of this set. Show that for a homogeneous cube, the ellipsoid of inertia at the center of the cube is a sphere, and calculate the radius of the sphere in terms of the density and dimension of the cube. Now we have two parts into this problem. One is we have to show that the cube is the radius, ellipsoid of inertia is a sphere, and calculate the radius of the sphere, radius of the ellipsoid of inertia in terms of the density and dimensions of the cube. The first part I think we have already discussed. Okay. Now, so we are doing problem number 7. We have a homogeneous cube which is, let us say, this one, okay, and of course we have depth of the, it's a 3D object. So we go to the center of the cube, okay, and we set our axis system there. Now because it's a homogeneous cube with some, okay, so let's, if I write the density as rho, it will be a bit confusing. So let's call it sigma, which is typically used for surface density, but it's okay for one example. So if each of the dimension of this cube A is A, then total mass of the cube is A cubed, sorry, total volume of the cube is A cubed, and then we multiply it by sigma to get the total mass m. Right. Now from the symmetry of the problem, we immediately see that I1, if I set these three axes, of course from the symmetry of the problem we know that this three axis, which is one actually goes through the middle of, okay, so this is not a very good drawing. So one axis will pass through the center of this surface, the second axis will pass to the center of this surface, and third axis will pass to the center of this surface. So basically one axis goes through the center of these two opposite planes, this will go through the center of these two opposite planes, and this one will go through the center of these two opposite planes. Okay. So if I calculate the moment of inertia of each of these axes, it will be I1 equal to I2 equal to I3 equal to some I. What is that I? I am not going into the details of that right now. Now, if this is the case, then this equation reduces to rho x square plus rho y square plus rho z square is equal to 1 by I. Okay. So, this is the equation of a sphere, right. So, the first part of the problem is we have already proved. So, that the ellipsoid of inertia of this uniform cube, when measured around when we set the origin at the center of the cube, we see that it is a sphere. That is proved. Now, second part is we have to calculate the radius of the sphere. Now, if you remember, the radius or the equation of a sphere is x square plus y square plus z square is equal to s square. So, this is the radius of the sphere for this particular spherical surface will be r equal to 1 by root I. So, our only job is we have to calculate I in terms of sigma and a, that is m essentially. So, I am just leaving it to you to calculate. You can take any of this, you can calculate I for any of this axis, it will be the same. Just calculate the value of I, put it in here, then you will find r equal to this. Also, I request you to calculate the radius of gyration for this I values. Okay. So, I will be equal for all three directions. Just calculate the radius of inertial ellipsoid and calculate the radius of gyration and try to see if there is any relation between these two. Okay. So, with this we conclude the discussion on this part of rigid dynamics. Now, it is time that we will move to the next part, which is Euler's equation. But before that, we need little bit of consideration in terms of we have to write some equations, we need to understand some physical properties. Okay. So, let us do that. Okay. So, first thing is right. So far, we have examined the rigid body sitting on the with respect to the space frame, as in all the dynamics. Let us say this is the rigid body in question. Okay, so we'll use this one maybe. So, this is the rigid body in question, and we have found out what is the dynamics, or we have wrote equations of the form n equal to dl dt. Well, strictly speaking, we have not done much with these equations right now, but we have seen that we can write equation that total external torque n is equal to rate of change of angular momentum, and that equation is strictly valid from the space set of axes. So, we will go back to our original notation. We will put x prime, y prime, sorry, it is said z prime for this space set of axes. And what we do is we attach with, I think we already discussed it, we attach another set of axes, sorry, another set of axes with this system which rotates along with the axis, along with the body. So, we have z, x and y, right. Now, let us try to understand what will be the form of this particular equation in the reference frame which is rotating along with the body. So, that means we try to try to write this equation in the body set of coordinate. Now, dl dt space will be equal to dl dt body plus omega cross L, right. So, if we, and this will be equal to n, or we can also write n external, total n external torque. So, this will be the equation if we are measuring things, angular momentum from a coordinate which is rotating with the body, with the rigid body, with a velocity omega. Now, if we set n external equal to 0, that means external torque equal to 0. Now if we are in the space set of system, so for space set of system this is the equation, for body set of system this is the equation, right? So if we set n external equal to 0, the first equation tells you that if n external equal to 0, then L is equal to constant. But for the second set of equation, if I set n external equal to 0, what do we get? We get dl dt plus omega cross L equal to constant. Now what we can do is equal to 0. Now we can take dot product, if I can take dot product with L from left hand side. So the first term becomes d dt of L square, and the second term actually gives you a 0, because in you can just do one step of cyclic permutation and you can write this term as it will be L omega, we have to do two steps of cyclic permutation, so omega goes here, so we can write this as omega dot L cross L, which will uniformly vanish. So this gives you, when you set n external equal to 0, sitting at the body frame of reference, you get L square equal to constant. Now, so if you are observing this from the space set of reference frame, then you get total angular momentum is a conserved quantity. But when you are observing it from the body set of axis system, that means if you are, as being an observer, rotating along with the rigid body, if you are also moving with the rigid body, then you do not get angular momentum as constant, but the magnitude of angular momentum is your conserved quantity. So this, in this case, it is the vector that is conserved, in this case this is a scalar that is conserved. Now with this knowledge, we basically extend this equation slightly and write three sets of equation which are called the Euler's equations of rigid body. Euler's equations of rigid body, right? So what are these equations? Okay, please note that these are sets of equations from written in body set of axes. Okay, and there are ways of connecting this with the, because finally we want to integrate and see what are the dynamics. For certain cases, of course, we are happy with sitting in the body set of axis, but certain times we would like to set ourselves in the space set of axis and see the dynamics from there. So of course the master equation is dl dt body plus omega cross L is equal to n external. Of course we can stop writing body because explicitly Euler's equation is in the body set, so we can simply try to reduce this in components. Now if we are going, so because we are in the body set of axis, and the principal set of axis will also be a part of one of the orientations of the body set of axis. If we write this set of equation in principal axis system, we will have certain advantage. So let's go to principal axis system, in which I, or rather in which dl dt will be, or rather I would start from beginning. What happens in principal axis system? We have already seen that L is equal to I1 omega 1 plus I2 omega 2 plus I3 omega 3. So it will be, let's call it x cap. Yeah, there will be x cap, y cap and z cap. So that means the angular momentum for each of this orientation will be so x component of angular momentum is a purely function of the x rotation, y component is purely a function of y rotation, and z component is purely function of z rotation. So that means we are killing all the cross terms in this calculation. So once we are in this particular reference frame, then we can write omega cross L as x cap, y cap, z cap, omega 1, omega 2, omega 3, okay, I1 omega 1, I2 omega 2, I3 omega 3, which you can find out is I3 omega 2 omega 3 minus I2 omega 3 omega 2 plus terms like this. So which can be written as x prime omega 2 omega 3 I3 minus I2 plus y cap. So just without calculating, just by symmetry of it, I can write that it will be omega 3 omega 1 I3 minus I2, right? So it will be I1 minus I3 plus z capped omega 1 omega 2 I2 minus I1. Okay, so these are the three components of this term, and the first term will simply give you, so if I put a dot here, so that means dl dt, it will be this one and this one, because I1, I2, I3, these are constants, right? So that is why we can simply put dots on the components of omega. Now, of course there is a vector sign here which I missed. Okay. Now decomposing this into three components, we can write this as I1 d omega 1 dt plus epsilon, if I decompose, it will be omega 2 omega 3 I3 minus I2 equal to N1. Similarly, we can write two more equations in the general form. I just writing in terms of indices, omega I dt plus epsilon I j k omega j omega k omega k minus omega j equal to Ni. So this is a more general form of it. So essentially we have three equations. We have written the equation for I1, and epsilon ijk is the standard Levi-Civita symbol, which gives you 1 if I, j, k are in cyclic permutation. So 1 2 3 2 3 1 3 1 2. If they are not in this particular order, this gives you -1, and if any two of the indices are equal, that gives you 0. So I think you are all familiar with the Levi-Civita function, and we all know that the cross product can be written in terms of Levi-Civita function. Okay, so these are my so this equation is not a single equation. This is set of three equations. One I have written explicitly here. This is the first equation. There will be second and third equation. These are called the Euler's equations. Okay. Now, once we have this Euler's equation, so we can also write it out in full, and also we can take up the case of torque free motion. Torque free motion means n equal to 0, that means n1, n2, n3 all equal to 0. Now, if we are dealing with a torque free motion and we are in the principal frame, please remember this equation is written out in principal axis system. If we are deviating from the principal axis system, then of course there will be additional terms into this equation and it will be not as simple as this one. Now, let us simplify it even more. Let us take up the case of torque free motion and write it out. So, in torque free motion, it will be simply I1 omega 1 dot equal to omega 2 omega 3 I2 minus I3, I2 omega 2 dot is equal to omega 3 omega 2 I3 minus I1, omega 3 omega 1 and I3 omega 3 dot is equal to omega 1 omega 2 I1 minus I2, right. So, these three are the equations we have in hand. That is for torque free motion and principal axis system, right. Now, we will make it even more specific, we will simplify it even more. We will take up the torque free motion for a symmetric top. Now, in symmetric top what happens? I1 is equal to I2, which is not equal to I3. So, instead of writing I1, I2 and I3, we can simply write I1, I1 and I3. Now, if we simplify these equations even more, and you immediately see that the last term will have a 0 in the right hand side. Now, if we simplify these equations little more for torque free motion of a symmetric top, then we see the equation becomes I1 omega 1 dot is equal to omega 2 omega 3 I1 minus I3, because I1 and I2 are identical. Okay. So, I1 omega 2 dot. So, I will just write out, I will replace all the I2s with I3s, okay, and omega 1 omega 2 I1 omega 2 dot will be omega 3 omega 1, this will be I3 minus I1, I3 minus I1, okay, and the third equation simply gives you I3 omega 3 dot is equal to 0, right. Also, the first two equation, you see that the right hand side is identical with there is a, of course there is a negative sign which is not placed here. I mean, I can just write this as omega 3 omega 2 omega 1 into I1 minus I3 instead of I3 minus I1. So, it comes with a negative sign, okay. So, if I reduce it, I mean if I slightly modify this, so what can I get is, we can reduce this equation to, from the first two equation I can write omega 1 double dot is equal to sum capital omega square or plus capital omega square omega 1 equal to 0, where this capital omega 1 is given by capital omega will be, okay, let us do it systematically, that will be easier. So, I can take the first equation and I can write I1 omega 1 double dot is omega 2 dot omega 3 dot I1, sorry, omega 2 dot omega 3 I3 omega 3 dot omega 2, right. Now, omega 3 dot from the third equation gives you 0, okay. So, we can set this equal to 0. So this will be I1 minus I3. Now omega 2 dot is omega 3 omega 1 I3 minus I1 divided by I1, and of course there is a I3, so it will be I3 square, right? Now this can be written as minus omega 3 square omega 1 I1 minus I3 whole square by I1, right? So take this I1 to the other side and you immediately get I1 square, or rather I1 to this side, so you immediately get omega 1 double dot plus omega 1 times omega equal to 0, where capital omega is this constant which is given by omega 3 square I1 minus I3 whole square divided by I1. And also please see that this equation directly gives you is omega 3 is equal to some constant, and we can set that equal to k. Okay, so this is my constant and my equation is this. Similar equation can be written for omega 2 double dot also, so it will be omega 1 omega 2 omega which is equal to 0, right? So we will have this these two sets of equation to solve and get a physical interpretation. I will do that in the next lecture. Thank you.